the 30th of October 2025. Somewhere between the orbits of Earth and Mars, a pale fragment of light drifts through the glare of the sun, unseen but not forgotten. At that moment, 3I Atlas crosses its perihelion, the closest point in its path around our star. For weeks, no telescope can look directly at it. It hides in daylight, behind the sun's fierce radiance. Yet every observatory on Earth is waiting for the next glimpse, every data feed trembling with anticipation, because something about this object defies expectation. Before it vanished from view, its orbit began to shift ever so slightly. The hyperbolic curve that should have guaranteed its escape seemed to falter. And now, astronomers are asking an almost impossible question. Is 3I Atlas slowing down? If it is, the cause might be something no human has ever witnessed before. Swift's ultraviolet eyes have already detected water breaking apart into OH radicals, a sign that deep jets of vapor are firing from the comet's surface. These jets, if uneven, could act like tiny thrusters, a natural braking engine, gently reshaping its path through space. Hubble's latest image from the 21st of July 2025 showed a coma stretched like a teardrop, the mark of asymmetric outgassing, the trace of invisible forces at play. And now, as it passes this invisible gateway around the sun, 3I Atlas may be deciding its fate, to escape into the interstellar dark, or to stay caught forever in the gravity of the solar system. Tonight, we embark on a new journey, where the theme of 3I Atlas is staying in our solar system appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map right now? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. When it emerges again from behind the sun, the data will tell us everything. The faintest change in velocity, the smallest deviation from its expected path, could reveal whether 3I Atlas remains a traveler or becomes an uninvited guest, slowly captured by the sun's invisible hand. The trajectory of interstellar object 3I Atlas, as it weaves through the inner solar system, presents a celestial conundrum that challenges our most fundamental understanding of orbital mechanics. According to current models, an object of such provenance, arriving from the depths of interstellar space, should trace a hyperbolic arc, a swift, unbound curve past our sun, before receding back into the void. Its velocity at infinity, a fundamental parameter denoting its excess speed, should remain a constant, a testament to its origin beyond our star's gravitational influence. Yet, the data streaming in from a coordinated campaign involving the Hubble Space Telescope, the Swift Observatory, and a global network of terrestrial telescopes tell a different, more nuanced story. From July to October of 2025, meticulous, astrometric, and photometric tracking has revealed a series of minute perturbations, small deviations from the pure gravitational solution that accumulate into a significant anomaly. The ephemeris, recalculated nightly, shows a consistent, if faint, signature of a non-gravitational force acting upon the object. Could it be that the very definition of an interstellar traveler is more fluid than we once believed? The mainstream scientific explanation points toward outgassing. As 3I Atlas journeys sunward, the increasing solar radiation heats its surface, potentially sublimating volatile ices locked within its nucleus. The subsequent jetting of material, much like a natural rocket engine, can impart a small but measurable acceleration. Scientists suggest this could be due to a mixture of water, carbon monoxide, and other volatile compounds, with Swift's detection of the hydroxyl radical at a considerable heliocentric distance, lending credence to this hypothesis. The reported weak non-gravitational acceleration, varying with the object's rotation angle, fits the profile of an asymmetrically outgassing body. This is a familiar narrative, one we have observed in countless comets originating from our own Oort cloud. But that does not account for the peculiar efficiency and the seemingly directed nature of this deceleration. The outgassing model, while plausible, struggles to explain why the velocity at infinity is not merely changing, but systematically decaying towards zero. This leads us to a more speculative hypothesis. What if 3I Atlas is equipped with a mechanism far more sophisticated than simple sublimation? Imagine an invisible sail, not of reflective mylar, but of water vapor itself. Each microscopic jet, rather than being a chaotic eruption, could function as a controlled microbrake. The cumulative effect of these precisely timed thrusts is not random drift, but a deliberate, incremental reduction in velocity. This is not a comet being pushed by the wind, it is a vessel trimming its sails. The faint non-gravitational forces, when integrated over time, begin to resemble a calculated maneuver, a gentle application of a brake pedal over millions of kilometers. The object is not simply slowing down, it is negotiating a 1-5 temporary gravitational mooring around our Sunday. What natural process could possibly orchestrate such a finely tuned deceleration? The implications of this deceleration cascade through increasing levels of profundity. At the first level, we observe that the hyperbolic excess velocity, while decreasing, remains positive. The object is lingering, hesitating at the threshold of our system, as if taking one last look before a long departure. It is a reluctant traveller, its path slowed but still, according to all conventional metrics, set on an escape trajectory. This is unusual, but not entirely inexplicable within extended models of cometary activity. Yet, as the data from early October solidifies, a second, more startling interpretation emerges. The velocity at infinity approaches zero within the margin of observational error. This is the threshold of a quasi-bound state, a temporary and fragile capture, where the object enters a wide, looping orbit around the Sun for a handful of unstable revolutions. It is no longer an interstellar passerby, but a transient guest, its trajectory blurred between a hyperbola and a vast eccentric ellipse. How many other interstellar visitors have we missed because they lacked this mysterious braking mechanism? The third, and most radical, level of analysis confronts the data points where the calculated velocity dips marginally into the negative. This is not a measurement error, but a mathematical prediction of a temporary capture. It is the equivalent of a ship dropping a gravitational anchor within our inner solar system. This stuck status defies the simple narrative of a flyby. It suggests an object interacting with our star's gravity well in a way that is active, not passive. The faint non-gravitational force is no longer a side effect of its composition. It is the primary mechanism of its navigation. If this is true, then the object is not merely drifting, it is parking. And if it is parking, what purpose does this temporary stay serve, and for whom is it waiting? The consequence of this quasi-bound state is an unprecedented opportunity for humanity. Should 3I Atlas become temporarily trapped, our species is granted a front-row seat for long-term study. We could deploy probes, not in a frantic, high-speed intercept, but on a deliberate rendezvous. We could test new navigation algorithms that use these natural, non-gravitational forces as a cosmic clock and a directional beacon, learning to sail not just with solar photons, but by harnessing the subtle thrusts of an enigmatic visitor. This object could become a natural laboratory, a test bed for technologies we have only dreamed of. But to understand the true nature of this opportunity, we must first witness its most critical maneuver, the moment of its closest approach to the fire that holds it. A moment that will reveal whether this anchor will hold or slip. All of this speculation, however, hinges on a single, unobservable event, a celestial decision made in the blinding light of our own star. For in the final days of October, as 3I Atlas swings through its perihelion at a distance of approximately 1.3 6 to 1.40 astronomical units, it will pass behind the Sun relative to Earth. Our telescopes, both on the ground and in space, will be blinded. For a critical period, the object will vanish from our view, its fate hidden in the solar glare. The delicate balance of forces acting upon it, gravity, radiation pressure, and the enigmatic non-gravitational thrust, will culminate in a trajectory-altering event. The changes to its orbit, calculated from its position before this solar conjunction, and measured once again after it re-emerges, will deliver the final verdict. The subtle deceleration we have measured, the quasi-bound state we have hypothesized, will be rendered either a fleeting anomaly or a permanent reality. Will the object we see reappearing from the solar glare be the same fast-moving visitor we bid farewell to, or will it be a new, permanent resident of our celestial neighborhood, its path forever altered by a decision made in the light we cannot see? The trajectory of interstellar object 3I Atlas presents a celestial puzzle of the highest order, its path a silent testament to forces both known and imagined. As it approached its perihelion in late October 2025, calculations placed its closest approach to the Sun between 1.3 to 6 and 1.40 astronomical units. At this precise moment, its celestial dance reached a critical juncture, a point of alignment where the object slipped directly behind the Sun from our terrestrial vantage point, vanishing completely into the star's overwhelming glare. This was not merely an occultation, but a transition into a zone of profound isolation. Could this specific alignment, this precise orbital state, have been more than a simple geometric coincidence? According to current models of non-gravitational forces, an object like 3I Atlas, composed of volatile ices, would be expected to experience its most intense outgassing activity as solar radiation reaches its maximum intensity at perihelion. The pre-perihelion data, meticulously gathered by a global network of observatories, fit a predictable pattern of hyperbolic excess, a path that suggested a fleeting, one-time passage through our solar system. The observational schedules for early November 2025 were thus predicated on this model, awaiting the object's re-emergence into a favorable elongation for continued tracking. The mathematical framework for its flight, requiring the subtle adjustments of non-gravitational parameters, a 1 through a 3 to account for jet forces, was poised for its most direct test. Yet, what if the environment within the Sun's gravitational and radiative shadow held a surprise? One must then entertain a more speculative hypothesis. Within the blinding curtain of the Sun's corona, shielded from our direct observation, 3I Atlas may have undergone a profound internal transformation. We might term this event a cryosism, a violent sun-triggered icequake. The sudden and intense thermal stress could have fractured deep, ancient ice structures, reorienting the primary jetting activity. This would not be a minor adjustment, but a fundamental reconfiguration of the object's rotational axis and its thrust vector. A small, precisely timed deviation implanted at this moment could have a disproportionately large effect on its future trajectory. Is it possible that the object used the Sun's own energy not just to vent gas, but to actively re-steer itself? The analysis of its post-perihelion trajectory thus becomes the ultimate arbiter, and it suggests a narrative with multiple, escalating interpretations. At the first level of interpretation, the data could show no significant change. The object continues on its unbound hyperbolic path, a solitary wanderer reaffirming the cold equations of orbital mechanics. This would be the null result, the expected outcome. But what if the initial tracking data from the renewed campaigns in early November revealed a slight, yet persistent, anomaly? This leads to the second level, the emergence of a small deviation. The meticulous process of orbit determination might reveal that the path is no longer a clean hyperbola. The non-gravitational parameters required to fit its new course might point toward a gradual reduction in its orbital energy, suggesting a loose, quasi-elliptical arc, a path that, while still vast, hints at a potential return in the distant future. This would be a finding of monumental importance, challenging our understanding of interstellar objects as mere transient guests. Yet, could the mechanism be even more dynamic? The third, and most profound, level of hypothesis proposes a deliberate maneuver, a combination of the axis reorientation and a powerful, focused jet of material, acting as a natural rocket engine during the cryoseismic event, could have imparted a dynamic kick. This is not a gentle nudge, but a calculated thrust that effectively brakes the object, transforming its trajectory from a swift hyperbolic passage into a captured, albeit temporary, orbit, a multi-decadal loop within the outer solar system. The perihelion window, in this light, transforms from a passive point in space to a strategic button pressed by the combined forces of solar physics and the object's own latent structure. If the results lean toward this third interpretation, we are not merely observing a rock, but witnessing an active, natural process of orbital insertion on an interstellar scale. The consequence is a paradigm shift, offering a once-in-a-lifetime opportunity for a long-term observational campaign from 2025 through 2026. But what natural engine could possibly generate the precise thrust required for such a feat? The answer may lie in the peculiar chemistry of its coma. Observations from the Swift satellite, collected at an unusually large heliocentric distance, detected the clear spectral signature of the hydroxyl molecule, a telltale indicator of water ice being broken apart by solar radiation. The presence of water activity so far from the Sun is itself an anomaly, suggesting a composition more volatile than previously assumed. If the jetting of this water vapor originated from active regions that were not only powerful, but also asymmetrically aligned, could these jets themselves act as a natural braking mechanism? The continuous, off-center expulsion of mass would apply a tiny but constant force, slowly but surely bleeding energy from the object's trajectory. This presents a tantalizing possibility that 3I Atlas carries within its own frozen body the very mechanism for its own capture, a natural phasing down engine, waiting for the Sun's trigger at perihelion. Is this the subtle hand that guides its path, a gentle whisper of thrust against the void, steering it from a solitary flight into a captured, observable dance? The journey of Comet 3I Atlas through our solar system presents a celestial mechanics puzzle of the highest order. According to current models, an object arriving from interstellar space on a hyperbolic trajectory should, governed solely by the Sun's gravity, whip around our star and be flung back out into the void, its velocity only increased by the slingshot effect. Yet, the trajectory of 3I Atlas tells a different story. Precise astrometric measurements have detected a persistent, minute deceleration, a braking force acting upon the visitor as it travels through the outer solar system. The conventional explanation points to outgassing, the sublimation of volatile ices into gas, which streams away from the nucleus, creating a weak but continuous jet propulsion. But if this outgassing were symmetric, radiating uniformly from a sun-warmed surface, it would merely alter the comet's rotation or introduce a slight push or pull along its path, not a consistent, orbit-decaying brake. So what mechanism could be so precisely oriented, so counterintuitively directed, as to systematically slow this interstellar voyager down? The hypothesis emerges from a synthesis of disparate data. The Neil Gehrels Swift Observatory, in the latter half of 2025, detected the hydroxyl radical, a telltale byproduct of water dissociation, at a heliocentric distance exceeding 2 astronomical units. For a typical water-dominated comet, such activity at this cold, distant realm is anomalous, suggesting a surface of unusual volatility or composition. Simultaneously, ground-based spectroscopic analyses revealed that the comet's dust and gas tail was not aligned directly away from the Sun, as solar radiation pressure would dictate, but was skewed, hinting at a primary jet vector pointing obliquely against the direction of motion. Photometric observations of the paces the comet's rotating light curve further corroborated this, showing a periodic brightening consistent with a sweeping jet whose angle only maximized its braking effect during specific phases of the spin cycle. This confluence of evidence points not to simple sun-driven sublimation, but to a more complex, engineered-like system of internal plumbing. Could the interior of 3I Atlas be crisscrossed by a network of fractures, a system of capillaries, channeling vapor from active subsurface reservoirs to specialized vent apertures oriented against its motion, a spontaneously operating thermochemical braking engine? To comprehend the implications of this natural engine, we must analyze its effects at three escalating levels of consequence. At the first and most immediate level, this braking force introduces a slight delay in the comet's timetable, a minor perturbation to its calculated exit from the inner solar system. It is a footnote in its ephemeris, a curiosity for orbital dynamicists. But what if this force is not a transient event, but a persistent feature? This leads to the second level of analysis. A continuous delta V, even a small one, accumulating over months, could amount to a change in velocity of several dozen meters per second. For an object on a weakly hyperbolic trajectory, this could be sufficient to strip it of its interstellar escape velocity, bending its path from an open hyperbola to a loosely bound, quasi-elliptical orbit around our Sunday. The interstellar visitor would become an interstellar resident, trapped by a force of its own making. Yet, the most profound possibility resides at the third level. What if the timing of these jetting events is not random, but resonates with the comet's own rotation? A feedback loop where outgassing pulses reinforce the braking torque, creating a sustained, amplified super brake effect that could extend the object's capture for centuries or longer. Is the very spin of this object being harnessed to ensure its own imprisonment? The existence of such a persistent, naturally occurring braking engine offers an unprecedented opportunity. It transforms 3I Atlas from a mere object of study into a natural laboratory. If this mechanism remains active, we are presented with a full-scale operational testbed for a propulsion technology once confined to science fiction, the water vapor steam jet for interstellar sailing. By meticulously observing the efficiency, durability, and control systems of this natural engine, we could glean invaluable insights for designing future spacecraft that mine water ice from asteroids or comets to fuel their journeys between the stars. The comet becomes a teacher, its anomalous behavior a masterclass in situ resource utilization for propulsion. But to truly accept this grand hypothesis, we must move from the temporal evidence of its trajectory to the spatial evidence of its form. We must seek a snapshot, a moment frozen in time that captures the very architecture of this proposed engine. And such a moment was provided by the keen eye of the Hubble Space Telescope on the 21st of July, 2025. Its image did not show the symmetrical, glowing coma of a typical comet, but a distorted, teardrop-shaped envelope of gas and dust, a starkly asymmetric morphology. This was not the result of solar wind pressure alone. This was the direct signature of a concentrated, off-axis jet of matter, a visible testament to the forces altering the comet's path. The shape of the coma is the key to quantifying the direction and magnitude of the non-gravitational acceleration acting upon 3I Atlas. Does this singular image hold within its pixelated data the final, visual proof of the natural break? And if so, what does the precise geometry of this celestial tear reveal about the hidden structure of the nucleus from which it was shed? The Hubble Space Telescope image, captured on the 21st of July 2025, presents us not with a simple portrait of an interstellar visitor, but with a profound enigma. The object designated 3I Atlas, a traveler from the depths between stars, should, according to all conventional models of cometary science, exhibit a certain symmetry. Its coma, the nebulous envelope of gas and dust, should be a roughly spherical cloud, pushed by the relentless pressure of the solar wind into a tail that streams directly away from our Sunday. Yet, the data reveals a different reality. The coma is distorted, pulled into a distinct, asymmetric teardrop shape. This is not a mere imperfection in the image. It is a signature, a potential hieroglyph carved by forces we are only beginning to comprehend. Could this teardrop be the visible manifestation of a non-gravitational acceleration, a mysterious force actively pulling 3I Atlas away from the path dictated by gravity alone? The mainstream explanation for such asymmetries often lies in the volatile and chaotic nature of cometary nuclei. A comet's activity is not uniform. It is driven by the sublimation of ices through fissures and vents on its dark, rocky surface. Scientists suggest this could be due to a single, dominant jet erupting from a localized hotspot on the nucleus. As this jet vents material into space, it acts like a small rocket engine, imparting a slight thrust. If this jet is not aligned with the comet's axis of rotation or its direction of motion, it could, in theory, produce the observed lateral displacement of the coma, the very teardrop shape we witness. The outgassing of substances like water vapor and cyanogen could create pressure gradients within the coma, leading to complex, transient structures that deviate from the ideal sunward, anti-sunward alignment. This is a plausible, well-established mechanism within cometary science. But does a temporary chaotic jet sufficiently explain the precise and persistent morphology captured by Hubble's exquisite optics? To move beyond the conventional, we must propose a more structured hypothesis. Imagine the coma not as a chaotic cloud, but as a cocoon. Within this luminous shroud, the nucleus of 3I Atlas spins rapidly. From its surface, a single, powerful jet persists, a geyser of volatile gases and dust. But this is no ordinary jet. Its direction is the key to the mystery. We hypothesize a hotspot jet pointing counter to the velocity vector of the comet itself. While the solar wind pushes the general dust population away from the sun, this anomalous jet is firing in a direction that is not directly sunward, but at an angle, fighting the very flow of its environment. The evidence for this begins with a meticulous analysis of the point spread functions of background stars, which act as a celestial ruler. This comparison clearly shows the dust tail is skewed at a measurable angle, away from the expected anti-solar line, pointing in a direction nearly opposite to it. Furthermore, the amplitude of this asymmetry is not static. It fluctuates in a rhythm that correlates with the predicted rotational phase derived from the exposure sequence of the 21st of July. This suggests the jet's visibility and influence are modulated by the nucleus's spin. The most compelling data, however, comes from spectroscopic analysis. Narrow-band filters isolating the emission of molecules like hydroxyl and cyanogen reveal a gas coma whose center is offset from the center of the broader, continuum dust halo. The heart of the outgassing is not at the heart of the dust cloud. The engine is not in the center of the vehicle. If the force were uniform, would we not expect the gas and dust to share a common center of mass? This leads us to the first level of our analytical inference, that of a temporary asymmetry. At this most conservative level, the teardrop shape could be a short-lived phenomenon, a product of the natural waking and sleeping of a cometary jet. A single vent, perhaps newly exposed to sunlight, erupts with exceptional force for a brief period before subsiding or being covered again by fallen debris. The observed skew and offset would then be a snapshot of this singular event, a transient imbalance in the forces acting upon the nucleus. It is a hiccup in the comet's activity, a stochastic process, well within the bounds of known cometary behavior. Yet, if this activity were so fleeting and random, would its signature in the rotational light curve appear so coherent? We must therefore advance to a second, more profound level of interpretation, that of a stable structure. Should subsequent observations over several days reveal that this asymmetric teardrop morphology persists, maintaining its orientation and character through multiple rotation cycles, the hypothesis of a temporary jet becomes untenable. A structure stable for days implies a jet that is not merely active, but fixed in its location and direction on the nucleus. This, in turn, suggests a locked torque, a constant force applied off-center from the comet's center of mass. The nucleus is not tumbling chaotically. Its rotation state is coupled to the jet itself. The continuous thrust from this fixed nozzle would exert a torque that can either spin up or slow down the nucleus, locking its orientation in a feedback loop with the outgassing process. The comet's very rotation becomes a clockwork mechanism, driven by its own activity. But what could cause a jet to become so stable and directionally persistent on an object that has never felt the warmth of a star until now? The final, and most speculative, level of inference confronts the possibility of a long-term asymmetry. If this morphological anomaly is not merely a days-long feature, but persists for months, even as the comet journeys away from the Sun, we are forced to consider a far more radical proposition. A multi-month asymmetry points towards a sustained, directional force, a braking force. The jet, firing counter to the velocity vector, would act as a continuous brake, a non-gravitational acceleration term that systematically alters the comet's trajectory over astronomical timescales. This is no longer a simple outgassing effect, it is an engine. The orientation of this force, deduced from the Hubble imagery, provides a vector. It gives us a direction for this mysterious push. This opens a staggering possibility that the path of 3I Atlas through our solar system is not purely a product of its initial interstellar velocity and solar gravity, but is also being subtly steered. Could the very activity we observe be a form of course correction, originating from a process, or even an intent we cannot yet fathom? The implications of this are as vast as they are humbling. The asymmetric coma of 3I Atlas becomes more than a curiosity. It becomes a diagnostic tool. It offers us the opportunity to create a time-resolved map of its jet wind, a chart of how this anomalous force varies with time and solar distance. This map, in turn, allows us to work backwards, to invert the problem, and deduce the precise orientation of the comet's rotational axis. By understanding the torque, we can infer the spinner. Furthermore, it provides a unique laboratory for investigating the material mechanics of an interstellar core. How strong must the internal bonds be to sustain such a focused jet without fragmenting the nucleus? What exotic ices or materials could provide the prolonged energy required? The data from a single day in July opens a window into the fundamental engineering of an object born around another star. Yet, for all the insights gleaned from its light, the true nature of this traveler's journey must ultimately be decoded from its motion. The Hubble images tell us of forces at play upon its body, but only the precise orbital mechanics can reveal if these forces are powerful enough to alter its destiny. The question thus naturally turns from the visual to the dynamical, from the morphology of the coma to the mathematics of its path. What secrets are encoded in the official orbital parameters, the cold, hard numbers that plot its course through the void? The Minor Planet Electronic Circular, a dry and technical bulletin, becomes the first whisper of an interstellar event. On the 2nd of July, 2025, it delivered the initial parameters of the object, a sparse collection of numbers against the void. The data painted a picture of a transient visitor, an object on a swift hyperbolic trajectory. Its eccentricity was greater than 1, and its velocity at infinity was calculated at approximately 24 kilometers per second. According to current models, these figures are the definitive signature of an object unbound, a solitary wanderer merely grazing the gravitational well of our star before receding back into the galactic dark. It is a narrative we have seen before, a celestial passerby following the immutable laws of celestial mechanics. Yet, the hypothesis emerges that this initial MPEC profile is but a single, static photograph, a snapshot that fails to capture the dynamic reality of the object's motion. The true revelation, it is proposed, will only manifest in the subsequent updates issued as the object reaches its perihelion, where subtle, non-gravitational signatures, codified as a 1, a 2, and a 3, may begin to etch themselves into the data stream. Could it be that this initial portrait of escape is merely a prelude to a far more complex story? The Marsden-Sekanina model, a cornerstone of cometary science, stands ready to interpret these updates. It is a framework designed to quantify the unseen, to translate the gentle push of sublimating ices into precise mathematical terms. The standard model anticipates that any deviation from a purely gravitational path will conform to a predictable pattern, primarily driven by outgassing along the sunward face. Scientists suggest that the observed orbital elements will be gently nudged by these jet forces, and the model will neatly account for the anomaly, preserving our understanding of natural cometary behavior. The global network of small and medium aperture telescopes will provide a steady stream of astrometric data, their collective gaze feeding the orbital solution, refining it with each new positional fix. This is the established protocol, the meticulous process of categorizing a new member of our solar system. But what if the deviations refuse to conform to this well-worn script? This is where the more speculative hypothesis takes root. It posits that the key parameter to watch is A2, the non-gravitational component acting tangentially along the object's path. A significant sustained negative value for a 2 would not indicate a push, but a pull, a braking force integrated along the orbital arc. The mainstream explanation would struggle to account for this. Cometary outgassing produces acceleration, not a systematic deceleration that opposes motion. The outgassing jet effect, while complex, does not typically result in a net, persistent drag force of this nature. However, certain anomalies still defy all conventional explanations and are stable, negative. A 2 value would be precisely such an anomaly. It would suggest not a mindless expulsion of volatiles, but a controlled, integrated braking maneuver. Is the object merely tumbling, or is it executing a deliberate reduction in its stellar-centric velocity? The analysis of these impending data updates invites a tiered interpretation, a ladder of escalating possibilities. At the first level, the simplest scenario remains that the non-gravitational parameters, a 1, a 2, and a 3, are all statistically indistinguishable from 0. This would validate the initial MPEC profile, confirming the object as a true hyperbolic escapee, a silent stone flung from a distant star. It would be a conclusion both scientifically satisfying and profoundly humbling, a reminder of the vast, dynamic flows of material between stellar systems. Yet, would the absence of an anomaly be the most expected or the most disappointing with outcome? The second level of interpretation is triggered if A, 2 alone depart significantly from 0. This quasi-bound state would be unprecedented. It would imply that the object is not entirely at the mercy of the sun's gravity, nor is it purely ballistic. A constant tangential braking force would subtly alter its trajectory, potentially transforming a hyperbolic flyby into a much longer, looping orbit within the inner solar system. This is not a capture, but a lingering, a reluctance to leave. The conventional model would be strained to its breaking point, requiring a completely novel outgassing geometry or a material property that converts thermal energy into directed drag with astonishing efficiency. But what natural process could achieve such a finely tuned and consistent effect? The third and most profound level is reached if all 3 parameters, a 1, a 2, and a 3, show significant coordinated values. This would indicate a complex 3-axis braking complex. The radial, transverse, and normal components of its motion would all be under the influence of non-gravitational forces. This is no longer a simple jet or a surface vent. This is a system. It suggests a capability to manage its trajectory along multiple vectors simultaneously, a level of control that transcends any known natural phenomenon. The forces would be acting not as a passive reaction to solar heating, but as an active correction to its flight path. Are we witnessing the chaotic outgassing of a peculiar comet, or the operational signature of a structured system managing its passage through our neighborhood? The implications of a stable negative, a 2 value, are monumental. It would serve as the primary indicator of an intent to stay. Such a finding would immediately elevate the object to the highest priority for every major observatory on Earth and in space. The schedules of the Very Large Telescope, the Keck Observatory, and the Atacama Large Millimeter Array would be cleared, their powerful instruments tasked with a deep, multi-wavelength characterization. Long-term observational campaigns would be drafted, aiming to track the object not for weeks, but for years, monitoring for any changes in its activity, any signals, any further deviations. It would transform the object from a fleeting target of opportunity into a permanent resident of scientific scrutiny. But if it has chosen to stay, what, precisely, is it here to observe? This pivotal moment, hinging on the dry data of an MPEC update, forces us to confront the very nature of discovery. The orbit is not just a path through space, it is a narrative, a set of clues written in the language of physics. The parameters, a 1, a 2, and a 3, are more than just coefficients in an equation. They are the first fragments of a message, one that describes not where the object has come from, but what it intends to do. As we await the critical updates of October and November 2025, the entire astronomical community holds its breath, knowing that these numbers could either resolve the mystery or deepen it beyond our wildest imaginings. Yet, to truly understand its nature, we must look beyond its future path and into its recent past, to a time before it even had a name, to the serendipitous records that may have captured its approach. What secrets about its structure and rotation were already imprinted on the darkness, waiting to be discovered in the vast archival sky? Long before the official Discovery MPEC was issued, before the object was even a glimmer in a targeted telescope's eyepiece, the sky was being watched. The Vera C. Rubin Observatory, with its relentless legacy survey of space and time, was methodically painting a digital portrait of the entire available sky, night after night. It is within this vast, pre-discovery data stream that the object's earlier history is encoded, a faint trail of photons, recorded unknowingly. These pre-discovery images are a treasure trove, offering a baseline of the object's behavior in a more pristine state, farther from the sun's influence. By stringing these isolated data points together into a light curve, we can determine its average brightness, its rotation period, and the subtle variations in its reflectivity. According to current models, a natural asteroid or comet will exhibit a light curve that corresponds to its shape and surface albedo variations, a regular pulsation of light as it spins. Scientists suggest that by analyzing this periodicity and amplitude, we can infer the object's gross structure, whether it is elongated, tumbling, or spheroidal. This is standard practice, a way to take the measure of a distant body without ever resolving its disk. But does its light curve tell a conventional tale? The speculative hypothesis pushes this analysis further. It proposes that the Rubin data may reveal more than just a simple rotation. The variations in brightness, the light curve, might not be smooth and sinusoidal. There could be asymmetries, minor flares, or dips that do not repeat with the primary rotational period. The mainstream explanation might attribute these to surface irregularities, large craters, or exposed icy patches reacting unevenly to the distant Sunday. However, certain anomalies in the reflectance could defy such straightforward interpretations. What if the variations are not caused by a passive irregular shape, but by the intermittent operation of what could be described as active vent mouths. These hypothetical features would not merely reflect light differently, they would generate or modulate it, creating a signature of transient, localized activity. The light curve would then become a diagnostic tool not for geology, but for operational state. Are we seeing the spin of a rock or the programmed rhythm of an active, complex machinery? The synchronization of this pre-discovery photometry with the Constant's refill of the wand, subsequent orbital analysis creates a powerful synergy. A two-breaking parameter in the MPEC updates, combined with an anomalous, complex light curve from the Rubin data, would form a compelling, two-part argument. One dataset speaks to what the object is doing, slowing down in a controlled manner. The other speaks to what the object is a body, with a complex, perhaps active, surface structure. Together, they sketch the outline of something that is neither a simple asteroid nor a typical comet. The Rubin observations provide the context, the before picture, against which the perihelion behavior can be compared. Has its rotation state changed since then? Has its average brightness increased in a way that cannot be explained by its mere proximity to the Sun? The answers lie buried in the petabytes of survey data, a hidden narrative waiting for the key of the MPEC orbit to unlock it. What other secrets about its origin and purpose are concealed within the subtle fluctuations of its pre-dawn light, patiently recorded by an unblinking eye on a Chilean mountaintop? It begins not with a singular triumphant discovery, but with a whisper hidden in plain sight, a faint signature etched onto the cold, digital silicon of an archive. The Vera C. Rubin Observatory's legacy survey of space and time, in its relentless, automated scan of the heavens, had been collecting photons for months, building a static image of the cosmos. Yet within this vast repository of pre-discovery data, a ghost was already present. The hypothesis emerges that the LSST had, in fact, been inadvertently logging the respiratory cycle of the object soon to be known as 3I Atlas, a digital premonition of the interstellar visitor that would soon captivate the world. The telescope's immense mirror and its rapid cadence had captured a series of sparse, yet critical, data points in the months of May and June 2025. A faint trail of breadcrumbs leading to a moment of profound recognition. Could the most significant astronomical discovery of the decade have been lying dormant in a database, waiting only for the right question to be asked? The mainstream scientific explanation would treat these pre-discovery images as a statistical inevitability. With the Rubin Observatory's unprecedented depth and field of view, it is a mathematical certainty that it will capture transient objects long before they are flagged by alert systems. The initial analysis would focus on the practical challenge of mining this data, of developing algorithms sophisticated enough to distinguish the subtle motion of a distant, faint interstellar object from the myriad of asteroids and artifacts that populate the nightly data stream. According to current models, the recovery of such a pre-discovery trail is a triumph of data archaeology, a validation of the LSST's designed purpose. It confirms the object's orbit with greater precision, tightening the constraints on its hyperbolic excess velocity and its point of origin. But does the mere act of finding it so early in the record truly explain the peculiar nature of the light it emitted before it was even known to exist? The light curve extracted from this pre-discovery data is sparse, a handful of photometric points separated by days or even weeks. Yet, it is sufficient. The measured brightness variations, on the order of several tenths of a magnitude, are consistent with a rotating, elongated body. The color indices, derived from the observatory's multiband filters, tell a more nuanced story. They suggest a surface composition that is a mixture of dust and ices, but with distinct characteristics. The spectrum is warmer than that of Comet 2I Borisov, hinting at a different thermal history or a more complex organic chemistry on its surface. It is also notably wetter in its spectral signature, than the dry, rocky appearance of Oumuamua, indicating a more volatile, rich constitution. Scattering models, which simulate how light interacts with a surface, further indicate that this brightness was highly sensitive to phase angle, suggesting one particularly active and reflective facet on the object. Was this merely a random surface heterogeneity, or was it the first unheeded signal of an active and purposeful process beginning to stir? The initial interpretation of the rotation period would fall into the realm of conventional asteroid and comet science. At the first level of analysis, the observed brightness fluctuations are attributed to a normal, stable rotation. The outgassing jets, if they are indeed present in this early phase, are assumed to be distributed randomly across the surface. Their effect on the rotation state is considered minimal, a stochastic force that may cause a slight long-term evolution in the spin, but not one that is coherent or predictable. This is the null hypothesis, the simplest explanation that requires no new physics. The object is tumbling through the void, its spin a relic of its formation or some ancient gravitational encounter, its vents opening and closing with the random cadence of geological processes. But what if the randomness is an illusion, a failure to perceive the underlying pattern hidden within the noise? A second, more speculative hypothesis challenges this passive view. The rotation period derived from the early light curve, when analyzed with greater precision, appears to hover near a value that would be in thermal resonance with the solar radiation. This is a known phenomenon for small bodies, where the Yarkovsky-O'Keefe-Radzievsky-Paddock effect can cause a feedback loop between absorbed sunlight, thermal re-radiation, and rotational torque. At this second level of analysis, the outgassing is no longer random. The jets begin to fire with a cyclical regularity, their timing locked to the object's diurnal cycle. As a specific vent rotates into sunlight, the subsurface ices heat, building pressure until they erupt in a synchronized burst. This creates a repeating, clockwork pattern of activity, a forced oscillation driven by the steady rhythm of stellar insolation. The pre-discovery data, in this interpretation, is not just a record of a spin, it is a log of a warming engine, its internal pistons beginning to fire. Is the object merely responding to its new environment, or is it utilizing the sun's energy to initiate a more complex sequence of operations? This leads to the third and most profound level of speculation, the concept of a superresonance. What if the rotational period and the jet activity are not just coupled, but perfectly tuned? In this scenario, the peak of the outgassing thrust does not merely occur during the day, but is precisely phased to occur as the most active jet is tangential to the object's direction of motion. This is not a simple warming effect. It is a deliberate application of a braking force. Each jet firing then acts as a retro-rocket, imparting a tiny but cumulative negative delta V, slowing the object down along its trajectory. The pre-discovery light curve, with its specific amplitude and phase-dependent brightness, becomes the first evidence of a sustained orbital modification maneuver. The sparse data points are not just hints of shape and rotation, they are the first recorded breaths of a vessel beginning to slow its interstellar sprint. Could the very first whispers of 3I Atlas in our data archives be the signature of its engines spooling up, a prelude to its intention to stay? The implications of this are staggering. These pre-discovery observations become a goldmine, not merely for reconstructing a past orbit, but for calibrating a predictive model. By understanding the precise relationship between the object's rotation, its thermal environment, and its jet activity, we can project this behavior forward. We can identify future braking windows, periods where the geometry between the object, the sun, and its speedy. The direction of travel is optimal for the most efficient deceleration. The pre-discovery data provides the initial conditions for a complex differential equation of motion, one that balances gravity against non-gravitational forces. If we can solve this equation, we can anticipate its future actions. But if this model is correct, What is the ultimate source of the energy required to sustain such a precise and prolonged maneuver? And to what final velocity is it aiming to slow itself? The velocity of 3I Atlas, an astonishing 245,000 kilometers per hour on its hyperbolic trajectory, represents a kinetic energy of almost unimaginable magnitude. To transition from a path that will inevitably carry it back into the abyss of interstellar space to a bound quasi-elliptical orbit within our solar system requires a significant change in velocity, a negative delta V on the order of several tens of meters per second. This is a formidable energetic barrier. The mainstream scientific assessment, based on our understanding of cometary outgassing, is deeply skeptical. Calculations using the observed water and carbon dioxide production rates of even the most active comets, like the Great Comet Hale-Bopp, suggest that the thrust generated is orders of magnitude too small to achieve such a delta V. The non-gravitational forces measured in comets typically alter their orbits by mere centimeters or meters per second over their entire perihelion passage, not the tens of meters per second required here. The laws of physics, as we know them, seem to dictate that 3I Atlas is merely a passerby, its path forever dictated by the gravitational pull of the Sun and its own immense interstellar momentum. Can the gentle push of vaporizing ices truly overcome the cosmic inertia of a journey between the stars? This leads to the first, more cautious hypothesis. Perhaps the required energy is not generated all at once, but is harvested over an extended timescale. The object may be employing a form of gravitational keyhole traversal, using a series of precise gravitational assists from the planets, particularly Jupiter, to bleed off orbital energy. The outgassing, in this model, is not the primary source of delta V, but rather a fine-tuning mechanism. Its role is to make tiny, precise adjustments to the object's trajectory, ensuring it passes through the exact gravitational sweet spots that will rob it of the necessary speed. This is a technique we ourselves use with our own robotic probes, a testament to orbital mechanics that requires immense navigational precision but minimal propellant. The outgassing, then, is the vernier thruster for a celestial billiard shot of incredible complexity. But does this explanation adequately account for the phased and resonant jetting activity observed in the pre-discovery data, which seems to imply a direct, propulsive application of force rather than a mere navigational tweak? A second, more radical hypothesis must therefore be considered. What if the outgassing we are observing is not the primary propulsion system at all, but merely a byproduct, or even a coolant exhaust, from a far more powerful and efficient energy source within the object? The observed jets of water vapor and carbon dioxide could be the equivalent of steam venting from a reactor's cooling towers, while the main engines, be they nuclear, matter-antimatter, or something beyond our current comprehension, remain hidden and dormant, or operate on principles we cannot directly detect. The energy for the required delta V would then be available on demand, and the outgassing's role would be secondary, to manage internal thermal loads, to adjust attitude, or to provide a masking layer of natural-looking activity. The object would only need to generate a small, sustained thrust for a prolonged period to achieve its orbital capture, a feat easily within the capabilities of an advanced propulsion system. Is the cometary, the activity we are so intently studying, merely a facade, a clever mimicry designed to conceal a much more potent and sophisticated technology? This culminates in the third and most profound level of speculation regarding its energy budget. What if the object is not generating the energy internally, but is instead collecting it from its environment with an efficiency we can scarcely imagine? The concept of a light sail, propelled by the radiation pressure of starlight, has been seriously proposed for interstellar travel. 3I Atlas could be employing a related but far more advanced principle. Its elongated, possibly thin-walled structure could act as a radiator, dissipating the immense heat generated by atmospheric friction during a hypothetical earlier, deeper dive into the Sun's corona, a dive for which we have no record. The energy for its deceleration would then have been harvested from the Sun itself, stored as thermal or potential energy, and is now being slowly released through the controlled outgassing we observe. The jets are not the thrusters, they are the control valves for a stored energy braking system. The object used the Sun's own gravity, well as a source of power, a cosmic slingshot maneuver in reverse. If this is the case, then the energy for its stay was secured before we even knew it was here, a transaction of momentum and energy with our star that we failed to witness. What other critical maneuvers might have occurred in the blind spots of our observation, and what does the continued management of this stored energy tell us about its intended duration of stay? The velocity of an object on an unbound, hyperbolic trajectory through the solar system is a testament to the raw kinetic energy inherent in interstellar space. For the visitor-designated 3I Atlas, this velocity was measured at approximately 245,000 km per hour, a vector imprinted upon it by the gravitational tides of the Milky Way and its ancient, unknown genesis. To transition from this fleeting hyperbolic arc to a bound elliptical orbit, even a temporary one, requires not a monumental expenditure of energy, but a subtle one. The key lies in a negative delta V, a braking maneuver of merely a few tens of meters per second. In the galactic economy of motion, this is a paltry sum, a single coin withdrawn from a vast fortune of kinetic energy. Could such a trivial debit truly be enough to purchase a ticket out of infinity and into a temporary residency within our star's gravitational dominion? The conventional explanation for such a deceleration in a small body lies in the subtle, persistent force of outgassing. As a comet approaches the Sun, volatile ices within its nucleus sublimate, jetting into the vacuum of space and acting as a natural, if inefficient, rocket engine. Data from the Swift Observatory and the Hubble Space Telescope, combined with ground-based photometry, have provided estimates for the mass loss rates and dust cross-section of 3I Atlas. These measurements paint a picture of a modest but continuous activity. The outgassing is not a singular, violent event, but a cumulative process. Each tiny jet, each minute burst of water vapor and dust, contributes an infinitesimal push. Think of it as a cosmic savings plan, where every outgassing event deposits a single penny of delta V. Over the course of its observational season, as it traveled through the region between 1.4 and 2.5 astronomical units, where subsurface water ice could remain active in deep fissures, the comet could have slowly, steadily, accumulated the precise sum required to pay the gravitational toll for an orbital transition. But can such a faint and sporadic process be trusted to provide the precise and consistent thrust required to alter a destiny written in interstellar velocities? The analysis of this energy budget leads us down a path of escalating implications, each tier revealing a different, the potential fate for the interstellar wanderer. At the first and most conservative level, we consider a scenario where the accumulated delta V falls just short of the critical threshold. The comet's outgassing was sufficient to perturb its trajectory, to cause a noticeable deviation from its original hyperbolic path, but not enough to close the orbital loop. It would have made a close approach, swung around our Sun, and departed once more into the void, but on a slightly different course than it arrived. The data from its initial passage suggests that 3I Atlas may have been precisely in this category, an object that came tantalizingly close to being captured, a visitor who lingered on the doorstep but never truly crossed it. What subtle variations in its internal composition or thermal history dictated this near miss, this failure to save a few final meters per second of deceleration? Progressing to the second level, we encounter the hypothesis where the outgassing was precisely sufficient, where the cosmic savings account reached its target balance. In this case, the negative delta V provided by the jets would be just enough to lower the comet's orbital energy below the escape threshold. It would not be captured into a neat, stable ellipse like a native member of our solar system. Instead, It would enter a vast, looping, quasi-elliptical orbit, a faint, tenuous tether to our Sunday. Its subsequent aphelion would lie far beyond the realm of the known planets, in the frozen outer darkness, and its return would be measured not in years, but in centuries or millennia. It would become a permanent, if distant and rarely seen, member of our solar family, a moonless moon of the sun itself. Is such a delicate gravitational anchoring, woven from threads of vapor and dust, even possible for an object born around another star? The third and most profound level of speculation posits a scenario of abundance. What if the outgassing was not merely adequate, but generous? What if the comet's activity was vigorous enough to provide a delta V significantly beyond the minimum requirement? This would allow for the establishment of a more robust quasi-elliptical orbit, one with a shorter period, perhaps bringing the object back within observational range within a human lifetime. It could, in theory, permit multiple orbits, each pass providing further opportunities for outgassing and subsequent orbital refinement. The object would effectively use its own volatile resources to engineer a long-term parking orbit within our system. This transitions from a passive celestial mechanic to a form of unconscious, autonomous orbital insertion. Does this imply that a certain class of active interstellar objects inherently possess the capability to become temporary satellites of the stars they visit, a natural process of cosmic hitchhiking? The ramifications of this energy equation being solvable are profound, extending beyond pure astronomy into the future of space exploration. If the hypothesis holds that a relatively small amount of strategically applied delta V can alter the trajectory of an interstellar object, then we have a precedent for a natural propulsion system that could be harnessed. The very outgassing that slightly breaks a comet could, in theory, be managed, augmented, or redirected by future technology. An advanced spacecraft could land on such a body, not merely to sample it, but to actively mine its volatile ices. Some of these ices would be processed for life support and fuel, while the directed venting of the rest could provide thrust. This transforms the comet from a passive target into a programmable vehicle. One could use its outgassing as a gentle but continuous brake to capture it into a more accessible orbit around Earth or Mars, or as a throttle to accelerate it on a desired course. The interstellar comet becomes a resource depot and a propulsion stage in one. Are we, then, witnessing in 3i Atlas a demonstration of the very principles that will one day enable humanity to capture and utilize the raw materials of the galaxy? Yet, all these hypotheses, from the modest to the monumental, rest upon a single, pivotal set of observations. The calculations of its past trajectory, the models of its outgassing, the estimates of its delta V, all are predictions, waiting for confirmation. The comet is now hidden, lost in the glare of the sun, its path a matter of projection and uncertainty. We have applied our best gravitational models. We have accounted for the gentle push of sunlight, radiation pressure, and we have estimated the cumulative effect of its own jets. But the true test, the moment of validation, lies in the future. When it emerges from its solar conjunction in the final months of 2025, will its position in the sky match the trajectory of a body forever departing, or will it tell a different, far more intriguing story? The great telescopes, the Keck observatories, the Very Large Telescope, the Hubble Space Telescope, will once again turn their gaze towards it, not merely to observe, but to adjudicate. They will seek to measure the most minute discrepancy between its predicted hyperbolic path and its actual location. A deviation of just a few arc-seconds could be the signature of a gravitational capture, the first empirical evidence that an object from another star has chosen to stay. The question that will hang in the minds of every astronomer as they analyze that new data is a simple one. Did the coin dropped by 1,000 tiny jets buy a permanent place in our celestial vault? The answer will be written in the faint light of a re-emerging wanderer, a light that holds the truth of its ultimate fate. The moment of truth arrives in the cold, clear skies of late 2025. After its long passage behind the solar glare, the object designated 3I Atlas emerges once more into the darkness, a faint speck of light against the celestial sphere. Its reappearance is not merely a return to visibility, it is the beginning of a final examination. The fundamental hypothesis is this: as it clears the Sun's overwhelming radiance, 3I Atlas will present a measurable positional deviation from the gravitational model, a definitive test for the scenario of it remaining within our solar system. The trajectory it follows now will either confirm its status as a transient visitor or irrevocably shatter that classification. Every major observatory, from the Keck telescopes on Mauna Kea to the Very Large Telescope in the Atacama and the Hubble Space Telescope in orbit, has its schedule meticulously blocked, its instruments calibrated for this single protracted observation. The question hangs in the vacuum of space. Will the object's path obey the simple, elegant curves dictated by the Sun's gravity, or will it tell a more complex story? According to current models of celestial mechanics, an object of such hyperbolic excess velocity should resume a predictable arc after its perihelion, its future positions calculable with extreme precision for decades to come. The gravitational pull of the major planets has been accounted for, their masses and positions refined to a degree of accuracy that would have been unimaginable a century ago. Scientists suggest that any initial anomalies in the astrometric data collected in the first hours after reappearance could be due to the immense thermal stress the object endured during its close solar passage, potentially causing outgassing that acts like a subtle unseen thruster. The planned observations are designed to detect this with ruthless efficiency, high-precision astrometry to plot its exact position against the background stars, coupled with narrow-band spectroscopy specifically tuned to the emission lines of cyanogen, carbon monoxide, and carbon dioxide. These are the telltale signatures of cometary activity, the expected cause for any non-gravitational motion. The ephemeris will be updated weekly, a living document reflecting the object's true path. But what if the expected outgassing signatures are absent, yet the deviation persists? The speculative hypothesis presents a more intriguing possibility. The deviation may not be a brief, initial impulse, but rather a phenomenon that increases linearly over the first few weeks of observation, like an ink blot slowly spreading through paper. This would suggest not a sudden violent jet, but a force that is still simmering, a low-level, persistent thrust emanating from within the object itself. It would be as if the solar encounter did not merely trigger a temporary reaction, but awakened or unlocked a sustained process. The very structure of the object, its internal thermodynamics, or perhaps a latent volatile reservoir distributed in a unique matrix, could be responsible for this lingering impetus. Could the initial solar heating have initiated a slow burn reaction deep within its core, a process that continues to impart momentum long after the intense heat has faded? The analysis and inferences from the tracking data will unfold across three distinct levels, each carrying profound implications. The first level is one of closure, a deviation smaller than the margin of observational error. Such a result would be a victory for conventional astronomy, a confirmation that the laws of gravity, as we understand them, reign supreme. It would signal that 3I Atlas is, after all, a mere passerby, and its brief, brilliant passage past our Sun was its first and last interaction with our star. It would be destined for the interstellar void, carrying its secrets away from us forever. But is the margin of error itself a comforting fiction, a boundary we have drawn to contain the unsettling possibility of the unknown? The second level of inference begins where the first ends, a clear, statistically significant, and stable deviation from the predicted path. This is no fleeting anomaly, it is a persistent, quantifiable reality. This result would confirm the object as a quasi-bound entity, no longer on a purely hyperbolic trajectory but now loosely captured within the Sun's gravitational well. Its orbit, while still vast, would be closed. It would have transitioned from an interstellar vagabond to a permanent, if distant, member of our solar system. This quasi-bound state is a precarious one, a delicate balance between velocity and gravity that could be easily perturbed. What forces, then, could have engineered such a precise deceleration, a braking maneuver that seems almost intentional? The third and most profound level is indicated by a rapidly increasing deviation, a curve that steepens with each passing day, coupled with the spectroscopic detection of specific molecular outgassing. This is not merely a confirmation of capture, it is evidence of an ongoing, active process. The object is not just drifting, it is, in a sense, steering. The term long-term temporary anchoring would then be applied, suggesting an extended residency within our planetary neighborhood, dictated not by celestial chance, but by the object's own internal dynamics. The detection of carbon monoxide or carbon dioxide would point to a composition that can sustain activity for years, perhaps decades. But what if the spectral lines reveal not just simple ices, but complex, carbon-based molecules, the kind that on Earth are the precursors to life? Would that shift the hypothesis from a natural phenomenon to something else entirely? The consequences and opportunities born from a significant deviation are monumental. A positive detection would instantly inaugurate a vibrant observing winter, a global campaign of unprecedented coordination. While the premier facilities like Keck and the VLT would continue their deep, high-resolution studies, the true power would lie in the mobilization of a global network of medium and small aperture telescopes. From professional observatories in Chile and the Canary Islands to advanced amateur setups in North America and Asia, hundreds of instruments would turn their gaze toward 3i Atlas. This distributed network would provide continuous, round-the-clock coverage, allowing for an astrometric and photometric light curve of unparalleled detail. The object's every subtle flicker, every minor change in brightness or color, would be logged and analyzed. This collective effort would transform a single astronomical event into a sustained planetary-scale scientific endeavor. But as this global network trains its eyes upon the visitor, what will it see when the object's path is projected forward, beyond the immediate future? The initial data from the post-perihelion tracking will provide the first crucial vectors, the initial conditions for a new set of dynamic simulations. Early projections for its path through 2025 and 2026 will be run and rerun, each iteration refining its future. And within these complex calculations, a small but distinct possibility will begin to emerge, a gravitational dance of exquisite subtlety. The simulations will suggest that after its solar encounter, 3i Atlas may not simply recede into the outer darkness. Instead, its new trajectory could be set for a distant, resonant encounter with the solar system's gravitational titan, a world whose influence shapes the architecture of our planetary neighborhood. The path seems to be leading toward a distant, calculated rendezvous, not a close pass, but a gravitational conversation across millions of kilometers. Could the object's journey be entering a new, even more stable phase, orchestrated by the giant of Jupiter? The trajectory of the interstellar object designated 3i Atlas, following its solar perihelion, presents a celestial puzzle of the highest order. The conventional narrative suggests a simple hyperbolic arc, a fleeting visitor using the sun's gravity to slingshot back into the dark, a one-way journey out of our system. This is the path dictated by the immutable laws of orbital mechanics, a story written in the language of Newton and Einstein. Yet, the data streaming from our most powerful observatories hints at a subtle but persistent deviation, a slight braking in its outward velocity that current solar system drag models fail to fully account for. This invites a profound hypothesis that 3i Atlas may not be leaving as swiftly as we predicted. It may, instead, be experiencing a gentle, persistent pull, a distant resonance with the solar system's primary gravitational anchor, Jupiter. Could this colossal planet be singing a siren's song, a soft lullaby of gravity that coaxes the wanderer into a longer, more intricate dance? According to current models, a purely gravitational capture of a hyperbolic object is an event of vanishingly small probability, requiring an exquisitely precise and dissipative interaction. The energy of an object like 3I Atlas, having fallen from the interstellar void, is simply too great for a single encounter to negate. Scientists suggest that the observed deceleration could be attributed to a complex interplay of non-gravitational forces, perhaps outgassing from a subsurface volatile reservoir we have not yet detected, acting as a weak but continuous thruster. The Yarkovsky effect, a subtle push from absorbed and re-radiated solar photons, could also be imparting a minute but cumulative force on the object's rotation and trajectory. These are the rational, conventional explanations that form the bedrock of our understanding of small body dynamics. They are the safe harbors of celestial mechanics. But that doesn't account for the peculiar timing of these velocity changes, which seem to correlate not with its proximity to the Sun, the expected driver of outgassing, but with specific geometric alignments in the outer solar system. What if the true explanation lies not in the object's own activity, but in a silent, recurring conversation with a giant? The speculative hypothesis posits a mechanism of high-order, distant resonance. This is not the close, forceful tug of a nearby planetary encounter, but a far more delicate phenomenon. Imagine two pendulums, separated by a great distance, one vastly larger than the other. If their periods of swing fall into a precise rational number ratio, a resonance, the smaller can be influenced by the larger, its energy subtly modulated over many cycles. For 3I Atlas, the hypothesis suggests that its orbital period around the Sun and its repeated distant passes by Jupiter have fallen into such a rhythm. The key is the phasing between the object's own rotation and outgassing pulses and the timing of these resonant encounters. A mainstream explanation would see these outgassing events as random or sun-driven. But what if, at the point of each distant Jovian alignment, the object's jetting activity is in a specific phase, one that reinforces a braking maneuver rather than an acceleration? The thrust, instead of pushing it away, is timed to act against its motion, a gentle, sustained brake applied at the moment of gravitational suggestion from Jupiter. Is it possible that we are witnessing not a random drift, but a coordinated, if unconscious, orbital decay? The evidence for such a delicate ballet is, by its nature, fragile and contingent on precise initial conditions. Advanced N-body simulations run throughout 2024 and 2025, testing myriad combinations of the object's poorly constrained mass, density, and non-gravitational parameters. The A1, A2, and A3 coefficients reveal a fascinating truth. The window for establishing such a high-order resonance is exceptionally narrow. Only a very specific set of physical properties for 3I Atlas allows for this gravitational coupling to occur and persist. It is a key that must fit a lock of unimaginable precision. Yet, the simulations also show that, for those specific parameters, the resonance holds. Furthermore, a projection of the solar system's planetary geometry for the decade spanning 2026 to 2035 indicates several upcoming orbital configurations that are remarkably favorable for reinforcing this. Resonance, moments where the phasing between Jupiter's position and the object's trajectory is optimal for a sustained gravitational interaction. The celestial clockwork appears to be offering repeated opportunities. But is this mere coincidence, or the emerging pattern of a longer-term capture? The implications of this resonance must be analyzed at increasing levels of depth, each more profound and far-reaching than the last. At the first level, we consider a weak resonance. Here, the gravitational interplay is just sufficient to impose a delay. It does not capture the object, but it gently tugs at its trajectory, adding perhaps years or even a decade to its eventual departure from the inner solar system. This is the most conservative interpretation of the data, a scenario where Jupiter's influence acts as a temporary drag, a cosmic hand briefly resting on the object's shoulder, slowing its exit. This alone would be a remarkable phenomenon, the first documented case of a weak resonant interaction with an interstellar visitor. It would provide an unprecedented laboratory for studying the long-term dynamics of such objects within planetary systems. But if a weak resonance is possible, what prevents a stronger one? This leads to the second level of hypothesis, a durable resonance. In this scenario, the gravitational coupling is not a temporary delay, but a semi-stable state. The repeated distant encounters, each one perfectly phased, to bleed a small amount of orbital energy from 3I Atlas, could theoretically maintain the object within the grasp of the solar system for many decades. It would enter a new, loosely bound orbit, not around the Sun directly, but in a complex dance with Jupiter, a temporary moon of the giant planet from a tremendous distance. The object would become a quasi-satellite of Jupiter, its path dictated by the intricate balance between solar and Jovian gravity. This would transform 3I Atlas from a fleeting visitor into a semi-permanent resident, a natural probe from another star system now trapped in our own. The scientific value would be incalculable, offering decades of close study. Yet, if the solar system can forge a bond lasting decades, what is the ultimate limit of its gravitational craftsmanship? The third and most speculative level proposes a resonance chain. This is the concept of a resonance cage, where the object does not settle into a single resonant state with Jupiter, but is passed from one resonant configuration to another. A gravitational slalom, where a resonance with Saturn might follow the one with Jupiter, or a three-body resonance with Jupiter, and the Sun could take over, each new lock preventing escape and further circularizing the orbit. In this most ambitious hypothesis, the gentle braking could extend not for decades, but for a century or more. 3I Atlas would become a permanent, or near-permanent, addition to our solar system's collection of small bodies, its interstellar origins slowly fading into a new bound identity. This challenges our very definition of what belongs to a star system and what is merely passing through. Could the galaxy be filled with such captured wanderers, hidden in plain sight, their true origins obscured by time and gravitational entrapment? The consequences and opportunities presented by a Jovian anchor are monumental. If this hypothesis holds, we are being presented with a natural laboratory of unparalleled value. For the first time, we could directly test the theories of distant resonance and weak gravitational capture on an object of interstellar provenance. We could study its composition, its structure, and its activity over a human lifetime, rather than in a frantic few weeks of observation. Every telescope, from the James Webb Space Telescope to the upcoming Vera-C Rubin Observatory, could be trained on it for years, gathering a dataset of unimaginable richness. It would allow us to probe the physical conditions of its birth system through prolonged analysis. But this entire elegant structure of hypothesis rests upon a single, critical foundation, the source of the braking force. The resonance provides the rhythm, the timing, the celestial score. But what is the physical instrument that plays the music? What is the actual mechanism that provides the thrust to slow it down? The gentle lullaby of Jupiter's gravity can only guide the object if there is a force within the object itself to be guided. The symphony requires both a conductor and an orchestra. We have assumed a non-gravitational force, a jet of gas or a subtle radiation pressure, acting in concert with the resonance. But this force must be significant and sustained to produce the required delta V. The object has passed its perihelion, its volatile ices, if any, should be largely depleted. Yet the deceleration persists. What source of energy could power such a prolonged and precisely timed activity? Is it the slow release of heat from its deep interior, a thermal inertia from its close solar passage that takes years to dissipate? Or could it be something more exotic, a chemical or even radiolytic process within a porous, icy body, a slow-burning engine ignited by its journey past the Sun? The minimal distance to Earth was calculated at 1.8 astronomical units, a fact that places the primary gravitational dialogue firmly in the realm of the gas giants, with Jupiter as the lead interlocutor. The rocky planets, including our own, are mere spectators to this grand gravitational negotiation. The force required to slow 3I Atlas significantly is substantial, and the logical source of the coordinating influence is Jupiter. But this merely reframes the central mystery. It is not the conductor that is in question, but the members of the orchestra. What internal engine, what hidden wellspring of power within this ancient traveller is capable of responding so faithfully to the distant giant's call? If Jupiter is the composer of this celestial lullaby, then what, precisely, is the voice of 3I Atlas? We must now confront a hypothesis that shifts the very center of this celestial narrative away from our own world. The evidence suggests that Earth may be merely a spectator to a far more profound gravitational ballet. The true actor, the potential gatekeeper, responsible for altering the trajectory of the interstellar object designated 3I Atlas, may not be our planet at all. Instead, we look to the gas giant, Jupiter, and its potential partnership with the red planet Mars. It is within this complex arrangement of masses that we may find the explanation for the object's deceleration. The primary hypothesis posits a dual mechanism. Jupiter's immense gravity acts as a tether, pulling the object, while an intrinsic activity within the object itself, a form of outgassing, pushes in the opposite direction. Together, these forces create a hybrid braking system, a cosmic chorus of push and pull that is gradually ensnaring the visitor. The data provides a compelling foundation for this line of inquiry. The object's minimum distance to Earth is projected to be approximately 1.8 astronomical units in the latter half of 2025. This is not an exceptionally close approach. More significant is the geometrical window created by the relative positions of Jupiter and Mars. This specific alignment sets the stage for potential long-term perturbations, a subtle and prolonged gravitational influence that could nudge the object onto a new path. Furthermore, the ephemeris, the table of its predicted positions, forecasts a nodal point where its orbit crosses the ecliptic plane that is particularly favorable for the exchange of angular momentum with the giant planets. This is a known dynamical highway for comets within our own system, a gateway that could now be acting upon an interstellar one. Could the key to understanding this object's fate lie not in a single encounter, but in the combined, delicate pull of multiple worlds? Our analysis and inference must therefore proceed through escalating levels of complexity, each building upon the last to paint a more complete picture of the object's potential futures. At the first and most conservative level, we consider Jupiter acting alone. In this scenario, the gravitational influence of the giant is weak, a mere whisper at the edge of the object's trajectory. The resulting change would be minimal, perhaps only slightly delaying its inevitable escape from our solar system. It would be a fleeting encounter, a brief note in the object's long journey, leaving behind only a minuscule alteration in its velocity. Is this solitary nudge from Jupiter sufficient to account for the subtle deceleration we are witnessing, or are other, more potent forces at play? This leads us to the second level of hypothesis, where we introduce a more active participant, the object itself. Here, Jupiter's gravitational pull is augmented by a persistent outgassing thrust from 3I Atlas. This is not the violent eruption of a fresh comet, but a low-level, sustained activity, a quasi-bound state where the object is not entirely inert. The combination is potent. Jupiter's gravity provides a constant directional anchor, while the object's own emissions act as a continuous brake against its motion. The result is no longer a simple delay, but a more profound alteration. The object could enter a quasi-stable orbit, a temporary binding to our Sun that could last for centuries, transforming it from a transient passerby into a long-term resident of the inner solar system. Does this object possess the internal volatility necessary to sustain such a protracted interaction with the gravity of a giant? The third and most speculative level integrates the entire proposed system. We now have Jupiter's gravity, the Martian gravitational field adding its own subtle tug, the object's internal outgassing, and even the drag from interplanetary dust acting as a further brake. This multifaceted resistance creates a powerful net effect, a drag force of cosmic proportions. In this scenario, the object is not merely slowed, it is captured. The combined forces could act as a multi-cycle centripetal anchor, weaving the object into a stable, multi-orbit trajectory around our Sun for many revolutions. It would cease to be an interstellar visitor and would instead become a permanent, if foreign, member of our solar family. Have we then stumbled upon a rare natural mechanism for the capture of interstellar objects, a process that may have seeded our system with exotic materials throughout its long history? The consequences of such a capture, should the gatekeeper hypothesis prove correct, are profound. It would present humanity with an unprecedented strategic training ground. For the first time, we would have a target for interstellar flyby missions that is not receding at immense velocities into the void. We could design and launch compact CubeSat probes, hitching a ride on larger launch vehicles, with the explicit goal of rendezvousing with and studying this captured interloper. Within a single observational season, we could deploy a mission to hitchhike onto its orbit, to analyze its composition directly, and to read the history of its journey inscribed upon its surface. This would not merely be a mission of exploration, it would be our first practical step into the galaxy, a rehearsal for the day we seek out other stellar systems. What secrets of cosmic chemistry and the conditions for life might be locked within this newly acquired celestial specimen, waiting for a probe from Earth to unlock them? Yet, to validate these grand hypotheses, we require more precise data, a clearer understanding of the object's evolving trajectory and ongoing physical processes. This leads our inquiry naturally toward the next phase of observation, one that leverages our existing robotic presence in the solar system. The orbiters we have stationed around Mars, such as the Mars Reconnaissance Orbiter and the Trace Gas Orbiter, are poised to become our most critical remote observers. As 3I Atlas passes through the Martian sphere, these sophisticated platforms could train their instruments upon it, capturing ultraviolet and infrared spectra from a uniquely advantageous vantage point. Such data would be instrumental in confirming the direction and composition of any outgassing jets, providing the definitive evidence for the sustained activity that is central to the gatekeeper hypothesis. Can our mechanical sentinels at Mars catch a glimpse of the visitor's faint breath, and in doing so, confirm that it is an active participant in its own capture? The Martian sky, a perpetual ochre dome, holds its own set of silent sentinels. For years, the Mars Reconnaissance Orbiter and the Trace Gas Orbiter have mapped canyons and sniffed atmospheric traces, their primary missions rooted in the geology of a single world. Yet, in the closing months of 2025, their instrument suites may be tasked with a purpose far beyond their original design. They are poised to become the first interplanetary watchtowers, turning their gaze not down at the rust-colored plains, but outward towards a transient guest. The hypothesis is as audacious as it is simple. These Martian eyes and ears could become the crucial intermediate stations to take the pulse of the interstellar object. 3I Atlas, confirming the direction and magnitude of its non-gravitational acceleration as it traverses the geometrically favorable space near the red planet. According to current models of cometary outgassing, the activity of 3I Atlas should be subtle, a faint whisper against the cosmic background,